Welcome to this explainer. I am so excited to share this with you today because we're looking at something that honestly, on the surface, seems incredibly simple, right? But actually, it's a massive engineering feat. Today, we're deconstructing the water tanker truck. You know, for procurement managers and fleet operators, buying one of these isn't just a simple purchase where you pick something off a lot. No way. It is a high-stakes engineering challenge and really a strategic technical partnership. Poor engineering on one of these machines can lead to catastrophic chassis fatigue, massive leaks, or worst-case scenario, complete structural failure. So we're going to break down exactly how these incredible vehicles are engineered to survive some of the most punishing environments on Earth.
Okay, let's dive into this. Here is our blueprint for today's explainer. We're going to start with the water challenge, move into the armor and tank materials, then look at the skeleton and structure, explore the heart, which is the pumping systems, and finally wrap up with the OEM workflow.
All right, Section 1, the Water Transport Challenge. To really understand this machine, we first have to understand the main antagonist of our story, the water itself. So the crucial point is that water is not a static load. It's a moving, shifting, active force. When a truck carrying thousands of gallons of water hits the brakes or takes a sharp turn, that liquid just wants to keep moving. This generates a massive amount of destructive kinetic energy known as the slosh effect. Think of this energy as constantly, actively trying to tear the truck apart from the inside out. It can completely destabilize the entire vehicle or honestly outright crack the solid steel wells of the tank.
And we absolutely have to respect the sheer mathematical scale of the weight involved here. Just as a rule of thumb, every 1,000 liters of water equals 1 metric ton. Let that sink in. Hauling a full load is literally like carrying a herd of elephants in the back. A manufacturer has to carefully calculate the tank volume to perfectly match the truck chassis' gross vehicle weight rating, or GVWR. If a buyer misses this, or, tries to overload a lighter chassis just to save a few bucks, they are practically guaranteeing severe engine strain and inevitable, super dangerous braking failure.
Let's move on to Section 2, Armor, selecting the tank material.
Now that we know what we're up against, let's start building our machine. We're beginning with its armor, the tank shell itself. This is your very first line of defense, and it entirely depends on what kind of water you're hauling. See, there's a really rigid dividing line between potable, meaning drinking water, and non-potable water, which is used for stuff like dust suppression or construction. You cannot, under any circumstances, simply convert an old non-potable tank into a drinking water vessel. Industrial tanks use these heavy-duty chemical anti-corrosion coatings inside, which present a massive contamination risk for drinking water. Potable water strictly demands food-grade stainless steel and highly specific, non-toxic piping.
Now, what's really interesting about this slide is breaking down the total cost of ownership across the three main materials used in the industry today. First, you have carbon steel, coated of course. This is your industry standard for non-potable jobs because it's got great tensile strength and a low to moderate cost. But, and here's the catch, it requires high-grade, multi-layer epoxy resins inside to stop oxidation, and you actually have to inspect and touch up those coatings annually to keep the rust away. Then you have stainless steel, specifically the 304 or 316L grades. This is your absolute go-to for potable water. It has inherent corrosion resistance, but it requires highly specialized TIG welding, that's tungsten inert gas welding, just to ensure the internal seams are perfectly smooth and completely free of contaminants. And finally, aluminum alloy. This is a premium, high-cost option, but because it has a significantly lower tear weight, it allows fleets in regions with really strict axle load regulations to haul higher water volumes per trip, which saves a ton of fuel. Just keep in mind, aluminum requires some incredibly advanced pulse welding techniques to get right.
Which brings us to Section 3, Skeleton, ensuring structural integrity. Moving inward from the shell, we reach the skeleton of the machine. This is exactly how we defeat that nasty slosh effect we talked about earlier. Listen, a cheap tank is just an empty metal tube. But a highly engineered tank, it has a complex internal skeleton made of multi-section wave-breaking baffles. These are these curved steel plates welded directly inside to compartmentalize the shifting water. Top-tier manufacturers use a process called flanging on these baffles. Basically, they bend the edges to create a rigid lip, which dramatically increases their rigidity so they can absorb all that kinetic energy without deforming. They also throw in internal manholes so technicians can actually get inside for maintenance. But the real magic? That happens underneath. The tank does not sit directly on the truck chassis. It sits on a subframe using a flexible connection of U-shaped bolts and rubber damping pads. This is brilliant, because if you're driving a water truck on a bumpy off-road mining site, the chassis needs to flex. This flexible mount ensures that the intense torsional stress of the chassis twisting isn't transferred straight into the tank shell, because if it was, it would rip the welds right open.
All right, Section 4, Heart, Integrated Pumping Systems.
So we have our armor and our skeleton. Now, let's look at the systems that actually do the heavy lifting, the heart of the truck. The working end relies on this incredible piece of mechanical integration called the power takeoff, or PTO unit. Instead of dragging around a completely separate, heavy, gas-guzzling engine just to run the water pumps, the PTO physically connects the pumping system directly to the truck's own powerful driving engine. It is an incredibly efficient way to harness the massive horsepower already sitting right under the hood to manage heavy-duty water distribution.
And let me tell you, that PTO powers some serious hardware. Standard on most trucks are self-priming centrifugal pumps, which are fantastic. They can actually draw water straight up from ponds or wells if you're out in the field. Then you have the high-pressure cannons. These are absolutely essential for serious dust suppression and firefighting, shooting water at ranges exceeding 30 to 50 meters. But my absolute favorite feature of a modern build has to be the pneumatic control system. Instead of someone hanging off the back of a truck manually opening valves, which is super dangerous, modern pneumatic systems let the driver operate the front sprays, rear sprinklers, and side nozzles using automated controls right from the cab. This is a huge safety upgrade, keeping operators securely inside the vehicle when they're on hazardous industrial sites.
And that brings us to Section 5, Evaluating the Manufacturer.
We understand the machine now, so let's zoom out and look at the specialized engineers who actually build it. Let's move to and see how this builds into a rigorous consultative workflow. Because an industrial-grade manufacturer doesn't just run a one-size-fits-all assembly line. It starts with Step 1, chassis compatibility analysis, perfectly matching your volume to brands like Isuzu or Howo so absolutely nothing gets overloaded. Step 2 is welding precision. You really want to look for automated longitudinal seam welding machines. Automated welding provides a level of deep penetration and consistency that manual welding simply cannot replicate. It completely eliminates those annoying tiny hairline leaks. Step 3 is intense quality control. Every single tank must undergo a high-pressure leak test and a full 24-hour water fill test before it's ever allowed to leave the factory floor. Finally, Step 4 is surface treatment. They literally sandblast the steel down to a strict SA 2.5 standard before any paint even touches it. This ensures the primer bonds perfectly, completely stopping that notorious year-one rust that always plagues the cheaper, rushed vehicles.
Plus, a truly professional OEM will also hold strict international certifications. We're talking ISO 9001 for quality management, ASME standards for pressure vessel safety, and even ADR dangerous goods protocols for things like emergency shutoff valves. And because these vehicles are highly specialized B2B tools, they naturally require customization. Depending on chassis availability, a proper custom build generally takes about 30 to 60 days. In that time, they can add insulation to the tanks to prevent freezing in Arctic climates or evaporation out in the desert. They can add integrated fire monitors to create a really cool dual-purpose vehicle or install advanced GPS and flow meters. Those are absolute lifesavers for municipal contracts that require precise logging of exactly where and how much water is being used. Which brings us to our final thought today. Procurement is ultimately all about balancing the initial price tag against the total cost of ownership. A cheaper tank, one made with thinner steel, manual welding, and poor internal baffles, it might save you some money today. But for sure, it is going to lead to a damaged chassis, severe rust, and incredibly expensive operational downtime tomorrow. So I leave you with this question to chew on. Is your fleet truly built for the long haul, leveraging top-tier material science and engineering? Or are you risking catastrophic failure just to save on the upfront price? Understanding the anatomy of these heavy-duty machines gives you the power to make the right choice. Thanks for joining me on this explainer, and keep learning.